Hi folks, it's time to talk about acceleration, but this time it's going to be a little more specific. We're going to be talking about uniform acceleration. Uniform acceleration can also be called constant acceleration. And what it means is that the acceleration is not changing, but that does not mean that the velocity is unchanging. In fact, generally, unless the acceleration happens to be zero, the velocity is most certainly changing. Let's suppose you have a uniform acceleration of 3 meters per second squared. Starting at 0, after 1 second, you're traveling 3 meters per second. After 2 seconds, you're traveling 6 meters per second. So the velocity is changing, but the acceleration is uniform. And so when we have uniform acceleration, that implies something really important, and that is that the velocity is changing at a constant rate, which means if you want to find the average velocity, all you have to take is the beginning velocity plus the ending velocity and divide by 2. It's really very, very simple. And using that idea and the other formulas of motion that we have from kinematics, we can develop a lot of neat little expressions that will help us to work our way through uniform acceleration problems. So if we happen to have uniform acceleration, and remember, these formulas do not work if the acceleration changes in any way at all. They don't work at all. Since we know that displacement is average velocity times time, that of course is always true, then that means we can replace average velocity with the initial velocity plus the final velocity divided by 2, which I changed to a multiplication problem instead of a division problem. And that is a really important formula. It has 4 variables in it. Remember, if you know any 3 of them, you can always solve for the 4th. And so that's a way to relate displacement to initial velocity, final velocity, and time. And that's our first of our new formulas. But we can go further than that. Since final velocity is initial velocity plus acceleration times time, you can see that right here. That's final velocity. Then we can replace the expression that we just learned with this new one. And that means that if we simplify it by distributing the 1/2 and distributing the t, well, vi plus vi is 2vi, multiplied by 1/2 is just vi times t. And then 1/2 at times t is 1/2 at squared. And so now we have an expression relating displacement with initial velocity, time, and acceleration. And again, if we know any 3 of those, you should be able to use your algebra skills to find the 4th. Write that one down. That's an important formula. Finally, if we take the acceleration formula, final velocity minus initial velocity over time, and solve it for time, we get this. And if we use that in our previous expression, we can replace time with this expression right here. This expression right here. So that means we have 1/2 times final velocity plus initial velocity times final velocity minus initial velocity over acceleration. Now if we multiply both sides by 2a, we get that it's a simpler expression of 2 times acceleration times displacement is final velocity squared minus initial velocity squared. If you're wondering where that came from, remember the old formula that you learned in Algebra 1 class, that if you take a plus b times the quantity a minus b. Now if you remember algebra, you know that generally when you multiply 2 binomials, you don't get a binomial unless it's very special, and this is that special one. What do you get when you multiply the sum and difference of the same numbers? That's right, the middle terms cancel out. You just get a squared minus b squared. And so that's where this came from, by having this times this gives us v squared minus initial velocity squared. So that's a very handy formula. Do you notice what variable is missing from it compared to the others? That's right, you see it. Time is missing. Now we relate acceleration, displacement, final velocity, and initial velocity. Any questions? Oh, wait, this is a video. I can't answer your questions. Sorry about that, but your teacher can. So let's use those to try to answer a question. A bicycle accelerated from 1.2 meters per second to 4 meters per second for 3.2 seconds. If it covered a distance of 43.6 meters during that time, what was its rate of acceleration? If we assume that it's accelerating forward, that'll help us work the problem. If we don't know what direction it's accelerating, we really can't do it yet. Remember, acceleration is a vector. So let's assume that it's accelerating forward. If the initial velocity is 1.24 meters per second, and the time is 3.2 seconds, and the displacement is 43.6 meters, then what we're trying to find is the acceleration. Remember, forward is our positive direction, and I always like listing the variable that we're trying to find as well as the variables that we already know. All we have to do is locate a formula involving those 4 variables, and as it turns out, we have one. It's this one. Displacement is equal to initial velocity times time plus 1/2 times acceleration times time squared. Now, how do I know to use that one? Well, take a look. We know displacement, that's here, check. We know initial velocity, that's here, check. We know time, that's here, and here, check, check. And so that means we can find acceleration. So let's substitute. You would have 43.6 equals initial velocity 1.24 times time, which is 3.2. I'm dropping the units when I'm putting them in an algebra equation, but we'll remember those units at the end. Plus 1/2 times acceleration times the time, which is still 3.2, squared. Now, why don't you take a moment, maybe pause the video, and see if you can work your way through that problem. Okay, you're back. Well, let's continue with the algebra here and see how we do. So we have 43.6 equals 3.968 plus 5.12 times A, if I've done my math correctly. Remember, you square the 3.2, then you multiply by the 1/2. Got that order of operations right. You should get that the acceleration, at least according to my calculator, it says that the acceleration is 7.741 in whatever unit we're using. Now, we had a subtraction here, and that would keep us to the nearest tenth, but that's still going to be 3 significant figures. And then 3 significant figures over here as this coefficient, we should round to 3 significant figures. And so our answer is going to be 7.74 meters per second squared. Remember, that's an acceleration. And that is how you work a uniform acceleration problem. Okay? Okay, let's see if you can work one through all the way on your own. So let's try this one. A car slowed from 23.6 meters per second at a rate of 2.44 meters per second squared while moving 34.1 meters. What was its final velocity? Pause the video and see if you can do this one completely on your own, and we'll be back whenever you restart it. Okay, you're back. First step, of course, is to list those variables. Let's see what we got. Well, the initial velocity is 23.6 meters per second. The acceleration is negative 2.44 meters per second squared. Yeah, it's slowing. If we assume that the forward direction is positive, the only way for it to slow is if the acceleration is negative. Remember, a vehicle or a person or anything that's moving slows when its velocity and its acceleration are in opposite directions. Okay? The displacement is 34.1 meters, and the question asks, what is the final velocity? I hope you got that far, because if you did, then you can go straight to finding the right equation. The correct equation, of course, is the one that doesn't include time. So that's 2 times acceleration times displacement is equal to final velocity squared minus initial velocity squared. Now I know in the formula I didn't have the F on final velocity. The assumption there is that whatever your present velocity happens to be the final velocity, but I can write it this either way. And so we write 2 times negative 2.44 times positive 34.1 equals the final velocity squared, don't forget that squaring, minus the initial velocity, which is 23.6 squared. Okay? Now if you had trouble bringing it up to this point, you can pause the video again and see if you can work your way all the way through the algebra. So on the left side here, we would have negative 166.4 equals final velocity squared, don't drop that squared, minus 23.6 squared is 556.96. Okay, notice I'm not squaring a negative number. This says something minus a positive number squared. Even if it said something minus a negative number squared, the negative number squared would be positive. So this is always a subtraction on this side for this formula because it's minus some number squared. And so we add that to both sides and then take the square root. We get V final squared is equal to 390.56. And so then we get V final is equal to, well, what do you think it is? Well, as it turns out, the answer, if you remember your math class, is positive or negative 19.76. And what's our unit? Meters per second. Now the question is, what do I mean by positive or negative? Well, first the algebra. A positive or negative number squared gives us a positive answer, so that's why we get the plus or minus. It's kind of like solving the equation x squared equals 9. We get x is plus or minus 3. But what does that mean in the physics world? Well, the idea is this. Let's suppose the reason this object is slowing down is because it's coasting uphill. Okay, so the car starts fast, but it's going slower and slower and slower as it coasts uphill. And then it starts sliding backwards down the hill. That makes sense? After a certain distance, let's say 34.1 meters, it goes from here, say, to here. Okay, that's the distance right there. Okay, at this point, it could be either still going uphill at 19.76 meters per second, or it might be going downhill at 19.76 meters per second. Since we don't know how much time it took, we actually don't know which one it is. We do know, however, that we need to round to the correct number of significant figures. Our original problem had a maximum of 3. In fact, all of them had 3. So our correct answer is positive or negative 19.8 meters per second. And that's what we circle. We don't know which it is. Now, if it gives you some more information, like the amount of time that it took, or that it's still coasting uphill, then you might be able to figure out what the rest of it is. That makes sense? Okay, you are ready to do uniform acceleration problems and get A's on those tests. Congratulations.